Cancer Center. We heard some really excellent talks from Dr. Bashir and Dr. Sirlin on MRI. And now we're going to do something a little bit different. We're going to talk about texture analysis, which is a technique that can be applied to MRI, but I'll talk mostly about CT this morning. I don't have any disclosures, but I do have some acknowledgements. A lot of the work that I'll be presenting was funded by multiple entities, including the Society of MSK, Society of Abdominal Radiology, and the NIH. And a lot of this work would not have been possible without a very long-standing collaboration I have with Dr. Simpson. She used to be at Sloan Kettering, but now runs the Simpson Lab at Queen's University in Kingston, Ontario. So without further ado, here are today's learning objectives. Develop a workflow to perform texture analysis at your institution. Identify challenges in obtaining reproducible texture features, and to assess the role of texture analysis in clinical practice. At this point, you may be wondering, well, why do I need to bother with texture analysis? What's the big deal? If we have to sort of summarize what we do as radiologists, we're interpreting medical images, we're identifying imaging features, and hopefully through those features in our training or referral to evidence-based papers, we can add clinical value with our diagnostic accuracy. However, you may be wondering, maybe I'm not as good as I should be, or I can't possibly be 100% accurate all the time. Can I use computers to improve how disease processes are detected? And there's been a lot of excitement on the use of artificial intelligence and a lot of fear as well that it will eventually replace us. But I'm not going to talk about AI today. I'm going to talk about texture analysis, which is sort of a technique that's been used before sort of AI exploded onto the scene for deep learning in radiology. We know that radiology images are digitized. And so if we can sort of conquer how we extract data from our large databases of digital images, we can really transform how we apply or how we practice radiology in the future. A couple of definitions. Radiomics is the broader term, and it refers to the field of research focused on developing biomarkers based on both quantitative and qualitative features from medical images to predict clinical endpoints, whether that is disease diagnosis, prognosis, or treatment response. Texture analysis, on the other hand, is just a subset of radiomics, which is interested in referring to the quantitative assessment of the variations in pixel values on images using statistical-based methods. And I'll go into some very concrete examples of this so that it's clear to everyone. I got involved in texture analysis with Dr. Simpson many years ago now, where we were interested in sort of identifying patients who were at risk for postoperative liver insufficiency. And so these were patients that our surgeons wanted to take to surgery and do a major hepatectomy, maybe a right hepatectomy for a large ACC or for multiple liver metastases. And you want to select the right patients. This is a major surgery. The remaining liver has to be sufficiently healthy to sustain the patient's life after surgery. And luckily, they're pretty good at identifying good surgical candidates, but every now and then the patient has liver failure and dies as a result of the surgery, and that's devastating. So we had 12 patients that had liver insufficiency at our institution over a certain time period. We found 24 matched controls for the type of surgery and the age and sex and everything else. And we looked at the texture of the liver parenchyma to see if we could detect subtle changes that distinguished these two populations. And we found that certain features like correlation and entropy were different for the two different populations, right? And if you really zoom into the liver parenchyma, you can see that at the sort of pixel level, there's some subtle changes. Now, the black spots here are the vessels that have been segmented out. So we have to look only at the parenchyma and not include everything else, including the tumors, when we look at texture analysis. Aside from the liver parenchyma, we can also look at the liver tumors themselves. So in this study, we looked at predicting volumetric response for patients who had colorectal liver metastases. So to perform this type of analysis, you have to draw a contour around the liver tumor, right? Now that you have the tumor alone, you extract all the pixels, put them through a feature extraction, and then generate a prediction model that can train on a subset of the data to say, okay, well, given this variations in pixel intensities, can we then predict who's going to have a good response or not have a good response, and then apply it to a validation data. And we had some success. We could predict within 20% the volumetric change on the first scan after chemotherapy. And you can see here again, when we zoom in, that the tumors that had higher entropy or appeared more heterogeneous seem to have a better response volumetrically after the first few cycles of chemotherapy, right? So texture analysis is just a way of measuring this heterogeneity and then applying these features to make certain predictions. Now, the features associated with texture analysis, there are plenty of them, but you can describe many features that go beyond texture, for example, morphological features like volume, shape, and geometric characteristics. So when we talk about texture analysis, we're really referring to first order and second order texture features. So first order texture features are mean and standard deviation, which you're very familiar with. Some of you may be familiar with skewness and kurtosis, which has to do with the peakness of your sort of histogram. But second order texture features is really where the excitement is. We're talking about gray level co-occurrence matrices or GLCMs, run length matrices. And these don't just take into account what the grayscale levels are, but where they are in space relative to each other, okay? So the best way to illustrate this is with a few diagrams. And this one is from Dr. Lubner, who's from University of Wisconsin, and wrote this excellent primer on texture analysis in radiographics in 2017. So imagine you have two regions of interest side by side here. If you actually count the different pixels of different grayscales, they'll actually be the same numbers of black, same number of medium grays, same number of dark grays with respect to each other, but clearly they look different to our eyes. So on first order texture analysis, your histogram-based texture features, these are equivalent. They're going to look exactly the same. But when you take into account where the different grayscale pixels are relative to each other, you see that obviously on the right, the similar grayscale pixels are more clumped together. Okay? So how do we actually calculate this difference mathematically? And the way we do this is through these matrices. And it's worth going to the weeds a little bit about texture analysis just for this one example, because this is a beautiful example that was written up by Usman Bashir a few years ago in AJR. Now imagine that your region of interest is this 6x6 grid on the top left, and that your grayscale levels can go from 1 for black all the way to 8 for white. And you ask, well, how often does the number 2 and the number 4 are actually adjacent to each other from left to right? So in this particular region of interest, it occurs 3 times. So in your gray level co-occurrence matrix, where you plot all the possible grayscale values from 1 to 8, where 2 intersects with 4, it occurs 3 times. And you can see that this matrix actually represents how often different pairs of combinations of grayscales are actually occurring simultaneously or next to each other. And then you can repeat this in different directions. This just happened to be in the left to right direction, and the top right is in the diagonal, and the bottom right in the vertical direction, and generate more and more matrices. Okay, and you can make these matrices bigger and bigger as you include more grayscales. But how do you turn this into a single value for a feature? Well, you do these mathematical operations. You just kind of sum up all these matrices. And this idea actually came about from Haralick back in the 1970s. Okay, so this was invented way before texture analysis was applied to medical imaging, because this was applied to other industries to measure, for example, the quality of steel or some other material after it was produced. So these are concepts that have predated medical imaging by decades. And we're just kind of recycling these ideas into medical imaging because they're digital now, and because we're dealing mostly with grayscale values for most of our imaging. So if this sounds abstract to you, it sounded abstract to me too. So I went to Metropolitan Museum of Art a few years ago, and I went in their modern art section and took some photos of abstract art. And I told Dr. Simpson, like, hey, can you use texture analysis on these abstract paintings and rate them according to increasing homogeneity? So some of you may recognize on the far right this painting, this color field painting by Mark Rothko, very homogeneous on a score of up to 1. It's nearly perfect, 0.89. And on the far left, we have Lee Krasner, and he made it look like a polity because they were partners. But this is on a far low scale of homogeneity, is rates of 0.54. But these other paintings in the middle, you would have a hard time sort of rating these from least to most homogeneous. But with texture analysis and with mathematical operations, you can do this very reliably, okay? And so they have other texture features like entropy, and notice that this goes in the opposite direction, but it's not inversely correlated perfectly because the two middle panels are not in the exact same ratings as homogeneity, right? So these are, even though some texture features are correlated to each other, they're not perfectly correlated to each other. So the more texture features you apply, the more you have a chance of describing heterogeneity quantitatively. So now that you have a sort of intuitive sense of what texture analysis entails, let's talk about the workflow. What would you actually do if you want to do this in your own practice? The first question is, what exactly are you trying to predict? Are you trying to predict pathology, perhaps histology like liver fibrosis? Are you trying to predict treatment response? And if you're predicting treatment response, is it going to be a continuous variable like the exact volumetric change? Or are you going to try to predict a category of response like partial response using RECIST 1.1? You can also try to predict survival, perhaps continuously in terms of overall survival. Perhaps you're trying to predict overall survival at 2 years, a specific landmark point, okay? So the first question is, what exactly are you trying to predict? And are you going to use a discrete or a continuous variable? The next question is, you've decided that this particular question is the most impactful one you have. Do you have the right patient population to ask that question successfully? And this is where estimating your sample size and getting involved with your statistician becomes very important. This is important before you even embark on the next step, which is where you actually do the texture analysis, right? So having sufficient patient is key because texture features can number in the hundreds. And when you have hundreds of features, hundreds of variables, and you only have a few dozen patients, the chances of overfitting really increases. And we'll talk about overfitting specifically towards the end. How many samples do you actually have for each study endpoint? If you're detecting, say, pathology, benign versus malignant, and 90% of your sample is malignant, maybe that's such an imbalanced distribution of patients that you may not be able to answer that question in a significant way. What imaging modality are you including in the study? Right? I've shown you so far some CT-based texture analysis. You can obviously use MRI as well, but mixing the two becomes a problem. You can't just include every imaging modality in the same study. Select one, and if for CT, either select non-contrast or contrast-enhanced CT, so that you don't have problems of reproducibility in your texture features. When you're first starting out, usually it's going to be a single center study. But eventually, you also want to move towards multi-center studies so that your results can become more generalizable, that it's not just specific to the imaging protocols at your institution, that the results can be applied to other institutions as well. Now that you have your questions that you've defined, you've identified the patient population you want to study, you're pretty sure you have enough patients to answer the question, you then get into the actual workflow of extracting the features. And the first step is to perform segmentation. I've shown you a segmented liver tumor before. Down below here, I'm showing you a segmentation of a pancreatic tumor. And many studies have historically performed manual segmentation. So you have your favorite software, whether it's open source or commercial, and you draw a contour by hand around the tumor of interest or the organ of interest. And this can be extremely time consuming. There are semi-automated tools that may be available commercially. And I think eventually we'll move towards automated tools as deep learning and AI allows us to extract segmentations reliably in the near future. So hopefully this problem of segmentation will eventually go away. But for the time being, if you're going to perform manual or semi-automatic segmentation, you have to ask, well, who's going to actually do it? Is it going to be a radiologist? Is it going to be a trainee? Is it going to be a non-radiologist that you train specifically to extract, say, the liver contour, right? We have people who work in a volumetric lab who perform liver segmentation for clinical practice to estimate tumor liver volumes after surgery. And they undergo a significant amount of training, so we can use them for research as well. What software are you going to use? You use something that's commercial, for example, TerraRecon, or something that's open source like ITK-SNAP. And be aware that sometimes some softwares will require some kind of image preprocessing, so you can't directly use the DICOM images into your segmentation, and that may affect your texture analysis as well. Now that you have your segmentation volumes, the next step is actually to extract the features. And when we first started many years ago, we had to sort of code everything using MATLAB. But there are commercial software such as TextRad is one that's been very popular in the literature. And you can go to the website and it describes very clearly what it's doing. Or you can go to open source software like PyRadiomics. And PyRadiomics is kind of sort of taking off because it is open source and there's been a lot of support in the community. It's based on Python, so somebody with a decent amount of Python experience can implement this relatively fast. So this is gaining more and more traction I've seen in the recent literature. So you've done the segmentation, you've extracted your features. I've told you that those features can number in the hundreds. And when you're dealing with hundreds of features, you run into the problem of overfitting data. And so one of the next step that you want to consider is, can you reduce the number of features being considered in your eventual prediction model? So one of the questions is, well, exactly how reproducible are these features under different conditions? Is the features going to be changed if you change the field of view or change the contrast injection rates? These are all real problems that have been identified, and I'll go into this in a few slides. You can also use supervised or unsupervised methods of feature selection. Unsupervised methods of feature selection is when you look for features that are very correlated with each other. So let's say you have 100 features, but 50 of your features are kind of redundant. They're kind of very highly correlated with the first 50, so you can just kind of drop them. Another way to do this is to do something called principal component analysis, where you kind of develop new variables that kind of best represent all the features that you have under your model. And these are a way to reduce the number of features so that you can then proceed to the prediction model without the fear of overfitting data. Supervised methods is when you directly tackle each feature against the outcome. For example, benign versus malignant liver tumor, right? So you test each feature individually, you just select the best performing features, like maybe the top 5, and then you move it on to the prediction model, which is the last step. And this is where you're trying to answer the initial clinical question, whether it's predicting pathology, predicting treatment response, predicting survival. Okay. You can select your texture analysis features or other radiomic features that could be quantitative or qualitative. So qualitative features could be the imaging features that are described by LIRADS, like arterial phase, hyperenhancement, or capsule. Maybe you're trying to predict microvascular invasion, and capsule seems to be present in the absence of microvascular invasion. So maybe you combine texture features with semantic features. Or you can combine them with clinical variables, like AFP levels for HCC. There are going to be different types of statistical models using classifiers, for example, such as random forest to support vector machines when the outcome is discrete, like pathology, like low-grade versus intermediate versus high-grade tumors. But when you're dealing with continuous variables, it gets very complicated. Let's say you're trying to predict treatment response continuously or survival continuously. You then have to get into sophisticated regression models or cost proportional hazard models for survival. And this is where, definitely partnering with the biostatistician early on, at the same time that you're trying to determine, do you have sufficient patients, sufficient endpoints to even ask the questions. You don't want to tackle this at the last minute, because then you may find out that, you can't be successful in your prediction model because you just don't have enough patients. The last 10 minutes, I'm going to talk about some pitfalls in texture analysis, and these include reproducibility, challenges with segmentation, generalizability, and biological validation. early on, it was kind of the Wild West when it came to texture analysis because every institution had come up with sort of their own in-house software. And even though they were referring to the same papers, for example, GLCMs under the Haralick texture papers, different institutions had anywhere from 6 to 72 different gray level coordinate matrices definitions, right? And you can see here that the numbers really varied for different types of features, both texture and non-texture features. And then when they applied their own software package to the same 52 lung nodules, right? So everybody shared this data set of 52 lung nodules, and they're like, okay, well, let's calculate our features. And they compared the features to each other with the same names. They found that the coordinates correlation coefficient, which is a measure of reproducibility, that is maximal at 1. When it comes to size, tumor size, they were pretty close to each other, like nearly perfect. But when you're talking about texture features, depending on the feature you're looking at, the median was around 0.8, but there was a very wide range, and some of them were really not reproducible at all. And just because you have a highly reproducible feature doesn't mean it translates to clinical utility here. So this was an early recognition that, maybe we should move towards having the same definitions, the same sort of software to do our texture analysis. Some tumors are just not very reproducible, or some features are just not very reproducible for certain tumors. This is a sort of retest study of CAT scans for rectal cancer patients that were obtained 5 to 9 days apart. And in this case, only 9 out of 542 features had passed the threshold of a concordance correlation coefficient of 0.85. So this is in comparison to over 200 features for lung cancer. So perhaps doing texture analysis in rectal cancer on CT is not such a great idea. It's a different matter altogether for MRI. So the parameters and conditions that affect feature reproducibility can include the time interval between the scan and the repeat scan, the differences in contrast timing, the imaging parameters in reconstruction across scanner models and institutions. We know that, just because we have a liver triphasic protocol at our institution doesn't mean it's going to be exactly the same if we go across the street at Cornell. We may have disease-specific variations that vary with time of day, or variations in human cardiac output or prandial state that could affect reproducibility depending on which organ you're talking about. So just to give you a concrete example, we looked at patients who had undergone CT in the portovenous phase by chance within 2 weeks of each other, right? So maybe the patient came in, had an original contrast-enhanced CT in the ER, and a few days later, we decided to do a triphasic liver, and we compared the portovenous phase to each other. Well, the difference between a routine CT in the ER and a triphasic liver is the contrast injection rate. You can go from 2 mLs per second to 4 mLs per second. And what we found is that the further contrast injection rates differed, the lower the number of reproducible features we found, depending on which threshold of concordance correlation coefficient we define as reproducible. So for the liver parenchyma, really suffered. When we extracted the features from liver parenchyma, the concordance correlation coefficient really dropped for a lot of the features when the contrast injection rate differed. For liver tumors, the number of reproducible features stayed higher, but still it dropped a little bit as the contrast injection rate changed. And we can repeat this question by pixel size and slice thickness and so on and so forth. Segmentation itself is human dependent for the most part. So this is a study looking at intra and inter-observer variability for manual segmentations of renal carcinomas. And you can see that the different contours here are not perfectly aligned, both on non-contrast CT and on contrast-enhanced CT. And that can affect the number of reproducible features. So in this case, they use a threshold of 0.75 to define reproducibility. And the inter-observer and inter-observer agreement really varied. It was worse for inter-observer agreement in general, as you would expect. What about overfitting? The idea of overfitting is that when you have so many features, when you throw so many variables at your prediction model, the chances of finding something significant statistically by chance increases. And so this is one of the biggest pitfalls that you absolutely have to be aware of. And And when you read a paper, definitely pay attention to this. The basic idea is, let's say that you have 100 different variables, and you don't have really a single hypothesis. You're going to test every single one of those 100 variables against the outcome. Well, you're essentially testing 100 different hypotheses. And if you have a p-value defined as less than 0.05 as being significant, the chances of you finding something by chance just increases by a lot. And you have to do something called multiple hypothesis correction. And a simple way of applying this is just dividing p less than 0.05 by the number of hypotheses, in this case 100, so your p-value now drops to 0.0005. In reality, it's not this simple. There's some corrections, such as the Bonferroni corrections or Benjamin Hochberg correction. This is something you have to talk to your statistician about before you get into your prediction models. So again, the general problem is that with small sample size and a large number of tested relationships, you're going to run into overfitting your data. And as an extreme, the authors of this paper took 21 patients with esophageal cancer that had survival data from one of the papers they reviewed. And they just generated 100 completely new variables. They call it 1 to 100. And they randomly generated numbers to represent the texture features. This is completely randomly generated data. And they applied this ROC analysis without correcting for multiple hypotheses. And they used a p-value of 0.05. And what they found is that the errors under the curve for all their variables range from 0.21 all the way to nearly 0.8. And 10% of these had prognostic power in Kaplan-Meier survival analysis. So from this completely random data that they generated, some of the features were significant statistically when they did not apply multiple hypothesis testing corrections. So basically, what I'm saying is a p-value of 0.05 is just too high when you're testing multiple variables at once. And this is one of the biggest pitfalls that you have to be aware of. And this kind of brought a lot of doubt into the community. It's like, okay, we have to get our act together. We have to really do this correctly when we're applying texture analysis to make some prediction models that's going to be sort of clinically applied. So that original paper where I only had 12 patients with liver failure compared to 24 matched control, we expanded that, did multi-center with 5 centers, 74 patients in each arm. Again, liver failure is still very rare after surgery, thankfully, but this is about as big as a cohort as we could get. And luckily, we found that texture analysis still was able to distinguish between patients at higher risk for liver failures and those compared to those that do not. But ultimately, this needs to be tested in a prospective setting to see, can this go into actual clinical applications? Finally, one of the last pitfalls or obstacles to adoption of radiomics is that often, we look at these omic features and we generate all these numbers, create a beautiful prediction model, but we don't know what it means. And identifying the biological meaning of radiomic features is one of the last gaps that we have to overcome. And some have done this. They've looked at texture features and tried to understand, well, is it related to the genes? Is it related to proteins? Is it related to necrosis? You can actually use texture analysis to investigate a very specific question that can have direct biological significance. In this case, microvascular invasion. We perform texture analysis at the border of an HCC. And the border of HCC is known to be important. That's where the microvascular invasion occurs. And we've known from other papers that when you have a clear and intact capsule, the chances of microvascular invasion or MVI is very, very close to 0. But when it's lobulated and ill-defined, the chances of microvascularization are higher. In this case, we use texture analysis to directly investigate microvascular invasion at border by limiting the segmentation to the border itself. And we found that there's some reasonable performance compared to AFP and compared to other clinical parameters, but this again requires more multi-center validation. So I'll summarize by saying that texture analysis is really a subset of radiomics that is used to obtain quantitative features describing pixel variations. Reproducibility and overfitting of data remain significant practical challenges in texture analysis and in radiomics in general. And I talked one of the learning objectives is, well, is it clinically applicable? Not yet. There's been a lot of progress, but ultimately we need to put these into tests in a prospective trial, usually sort of as a correlative study to a, say, pharmaceutical trial, to really say that it's ready for prime time. So I'll stop there and I'll be happy to take any questions.